Hello, namaste everyone. In this video, we are going to learn how to prepare bathymetric map using QGIS and also to calculate the accuracy of the prepared map. So let's begin by knowing what is the bathymetric map. So basically, bathymetry is the study of underwater depth in oceans, lake, or other water bodies. And bathymetric map visually represent the underwater topography of that region by showing its depth variation through different kinds of color, contour lines, and 3D imagery or shadings. And these maps are very essential for marine navigations or geological extractions works and oceanographic research, fisheries management, and other environmental monitoring work. So for preparing this bathymetric map, we require a different kind of data. One of the important data for this is the bathymetric survey data, which is collected using technologies such as a sonar system and a satellite image and other type of radar image, I think, and other are the underwater vehicles are also used for the preparation of those bathymetric data. And these maps help to reveal underwater features like the sea mountains, trenches, and reefs, providing insight into the ocean current, sediment, and distribution, and seafloor geology as well. So, for the preparation of the bathymetric map, uh, there are different kinds of methodologies. One among them is using the interpolation, and the interpolation can be done in the two ways. One is the inverse distance weighting method, and another one is kriging tool. So inverse distance weighting method basically assumes that the values at a given location can be estimated by considering the values at the surrounding point, with the closer point receiving more influence than those far away. And this method calculates the weight based on the inverse of the distance between the known point and the unknown point, which is called as the point of interest as well. And IDW is relatively simple and computationally less intensive than the kriging tool. Whereas the kriging is a geostatical interpolation method. This considers both spatial autocorrelation, correlation between points at a different location, and the variance of the dataset to make the predictions over the another points. These involves modeling the spatial dependencies structure using a variograms which quantify how spatial correlation changes with distance. And this method then generates the prediction by weighting the known values based on the spatial structure. Kriging can be more sophisticated and flexible than the inverse distance weighting method. It is particularly useful when there is a need to account some spatial pattern, anisotropy, and when there is a desire to minimize the predictions error by considering the spatial correlation structure of the data. So we will use QGIS version 3.28 in this exercise to prepare the bathymetric map, and we will use these kinds of data which were collected using sonar in the lake, which have collected that longitude, latitude, and the depth point at that location. And we will validate the interpolated map with the observed point using a root mean square error, which measures how much error there is between the two datasets, that is measured dataset and interpolated dataset. Now let's begin with the exercise. For this, we will use QGIS 3.2 that I have already discussed. So we are now opening the QGIS. So we can use a new project, but I have a similar kind of project. So I am using in this project to prepare the map here. So I will prepare a new map. As I have talked previously, we will be using this data, location data and the respective depth data that was collected using sonar in the lake will be implemented to prepare the bathymetry map in this study. So this is the Excel CSV file. We will importing this into the QGIS interface and preparing a interpolation map. So let's do it. For this we have to import a text delimited layer from here. Now we will move towards, this is the point which I have shown sometime before. This is the depth data. So we will open this and we will put the x pad x field as a longitude and y as a latitude, and we will put z values as a depth and then add this to the map. So these are our depth point. So where this point falls we can know by adding a base map on this. I'm going to add a Google satellite hybrid image here so that we can know the boundary of the lake. So this is Khaste Lake somewhere in Nepal. So this is the bathymetry data and we will be using this. So first of all, I want to save this layer as a save file layer because it is in the Excel format. So I want to save this as a save file format at first. So I will save this as a depth data. I will keep the uh, coordinate reference system as this UTM zone 44, which is used for the western part of Nepal. So I will save this. So this is our data in zip file format. I will remove this CSV file from here. Now we will split these depth data into train data and test data so that we will use train data for modeling purpose or the preparing the interpolation map, and we will use the test data for the validation purpose. So I have already said that we will use the RMSE value. So RMSE value will be calculated using that test data. So first of all we will split this data into two sets. For that we will use the random selection tool, these two, and we will input uh, depth data and we will consider percentage of feature, and we are going to use 30% of the data as our test data. So it will select random 30% of the points from these all points as a test data. Now we will save these points, save selected feature as test data. So I will save this, and remaining data I will use the invert feature selection tool from here. So these are another 70% of the data selected here, and I will save them as a train data here. Now these are test and train data both selected, both are here into the different layers. Now we can use train data for the interpolation purpose. For this we have to use the processing toolbox here, and we will found the interpolation. and we will use we have the vector data as a point shape file, so we will use this saga tool. No, sorry, we will be using this grass tool, b dot soft dot rst, no idw. So we will use this tool and we will use train data, and we will keep this value. This is the number of interpolation points, means how many number of the neighboring point will be used or will be considered for using the idw method to interpolate the next unknown value. This we can put the default. We can put this values power parameter as default, and we have to use here the depth data, so that it will use the depth column for the interpolation purpose. So we can select the extent. For that, we have to add here another layer, which is the lake outside boundary. So I will add the lake boundary file from here. So there is a lake boundary. I will open this and add here. So we can select the extent, calculate from layer, and there is lake layer, and we can use the pixel value as per requirement. Here I'm going to use lake is in a small size. I think it is not very much big, so I will be using 5 meter as cell size here, and all these things will be kept by default, and I will run the code. So here we can see the interpolated map prepared. Now we can clip this layer, but first we will put this in this color format. So this is the bathymetric map, interpolated map prepared, and we will use lake map here. We can make this visually something more attractive. We will clip this feature within this range by doing this. So this is the lake area only, and this is the bathymetric map. So these are the training data set, these are test data. As I have already said, we will use these test data for validation purpose. So if we look in the attribute table of this subset, there are a total of 54 data set here. So we will know, I think there are 55 data set here, which is 30% of the total data set. Now we will use tool which will insert these raster values, as we know these are the interpolated or something predicted values will be extracted to a new column into this test data set. So we will use point to values, no values to point, I think. Yes. So there is a tool, add raster values to point. So I will use this tool, and here test data, and I will choose. So this is the map interpolated I did currently prepare. So I will this. So I will run this feature. So here is the result. we can see the attribute table. There is the depth data, which is measured data, and interpolated data, which is the predicted data by our IDW interpolation method. So we will use interpolated depth, and this is known as the predicted, and this is observed data, and we will use formula here mentioned RMSE of predicted minus observed squared summation, and there is divided by n, and the whole square root of this value will provide us the root mean square value, which measures the error of this prediction. So for that, there are two techniques. We can select all the data by this method. We can copy selected layer from here. We can go to Excel and we can calculate RMSE value. But I'm going to calculate these layers here. So for this, I will be going to the raster calculator here. I will create a new field as RMSE1, because it is not the whole process cannot be completed in a single step, so I will use this as 1. So this will be a decimal point. I will use precision up to 4 point. So the formula is predicted minus, so here we can see predicted minus observed square and summation. So we will use up to this step in this column. So it is open a bracket. So INTAR interpolate minus, so I will use this minus here, minus depth, which is observed value, and square of this value, which means this part of the formula. After that, we are going to sum these all values and divide by the total number of the observation. So this will provide us this value. Here you can see the one of the result, preview result here. So it will calculate all the values. Sorry for this. Oh, I have selected single layer, so it provided only a single layer value. So I will discard this, and I will deselect all layers from here. So I will go here again, do the same thing. RMSE1, I will use decimal real number, precision up to 4. So I will do INTR interpolate minus the observed depth, then square of this. This is okay for now. So in the next, we have to sum these all. So sum divide by n, I will do sum divide by n. So I will put this name. So this is just for example, so you can use these operation into the Excel sheet as well. So this sum means I'm going we have calculated p minus o square whole square, and we are now doing the summation of these values. Sum of RMSE1. So this is 3.61. So if we do divide by n, then we can put is divide by, we have already known there are total values 55 here, so it is 55. So this is 0.66, and if we do sqrt of all the values, then we can get the RMSE value. Oh, sorry again, I just forget to keep, sorry for this. We will do it again because I forget something here. RMSEFINAL. So I just forget to keep this as a decimal number. So I will put this, and we will keep sqrt square root of sum of RMSE1 divided by 55, and this is our final RMSE value. This is, so this is very much accurate. So we can check this into the Google. RMSE value. This means, so RMSE value between 0.2 and 0. Shows the model can relatively predict the data accurately. So you can see it is good. So this is all. We have prepared map as well as calculated the accuracy of the model. So after this calculation, I have here already prepared some of the maps out of this here. So in this layer, I have prepared a counter map by using the interpolated layer. These are the counter lines and counter polygons. After that, and we can also make these layers into the 3D format, and we can show a 3D visualization of the layers like this, which I think is very effective to present as well. So this is the layer. Yeah, we can see this is final map. So I can make another video so how to prepare the 3D image of the model. So if you are interested to learn how to make these 3D image out of the interpolation map, so please comment here and I will make another video of that as well. So thank you for now. I will stop here.